Hey guys, welcome to our first lecture for Chapter 5. We're talking about metabolism, ground rules for metabolism. Nothing too fancy just yet, but a good foundation for it at any rate. So let's jump right into metabolism, something people care about. So your book starts each chapter, with this a little engaging story or something, and this one's kind of, I don't know. I kind of want to use the word funny, but I also feel like a mean person if I say funny. It's a toast to alcohol dehydrogenase. Nice punny title there. It talks about the liver and all of the super important jobs that it has with blood sugar and immune system jobs, and then, of course, breaking down toxins. And it shows all these kids at a tailgate party or some deal like that. So it's sort of interesting because then they end your chapter with this picture of this guy who's in liver failure. So when we look at metabolism, which is what we're going to look at all chapter, a lot of it's breaking things down and building things back up into something useful. And some of the things that we break down are toxins. And some of them we know we're getting, and some of them we don't really know we're getting, but our body tries to deal with them just the same. So, our liver, we have a variety of enzymes, and one of them is called alcohol dehydrogenase, and it will break down ethanol. That is the alcohol that is in, beer, wine, your hard liquors. It's all the same. Ethanol is the alcohol that's in it. It's the same stuff that we mix with our gasoline that we make out of corn for our automobile engine. Same stuff. So the thing about alcohol is it's poisonous to to you and I. It's toxic to living things, and so when someone's drinking a lot of alcohol, the liver is trying to break it down with these enzymes, and as it's trying to break it down, it's using so much of its energy and so much of its oxygen to break down those alcohols that it's not doing its normal jobs that it should be doing as a healthy liver. And so over time, as the liver is continually abused by someone who's continually binge drinking, it will eventually harm and kill liver cells. Your liver has the cool ability to grow a little bit and to divide more cells to try to make up for it, but even that has its limitations. So eventually, the liver cells will start to die and they will start to get diseased. And in some of the cases, you get fat gets to accumulate as these large globules of tissue in the livers of heavy drinkers, and you can get alcoholic hepatitis or you can get cirrhosis of the liver, and both of these diseases can eventually lead to your total liver failure. And once the liver fails, your options are very limited. You either get a liver transplant or you die, and there's not a lot of middle ground. Unfortunately, there aren't many liver donors, and it's difficult to get a donation for a liver if you're a career alcoholic, for lack of a better term. So, top left, the healthy liver of a human. Bottom left, a diseased liver of a human who has done a lot of drinking. And then this picture is this fellow in your book who died at the age of 22 because he had done enough binge drinking to turn his once healthy liver into this, and without a transplant, he eventually stored up a ton of bilirubin, which accounts for the yellow color of his body, especially in his eyes. And that means his liver's not working, and his liver shut down, and he died from it at the age of 22. So take it easy with the alcohol. That's, I guess it's the intro to the chapter, so there's that. Let's look a little bigger scope than just one organ in one human. Energy is a big part of what we're talking about with metabolism. Energy is needed to sustain life's organization, and it requires really ongoing energy inputs. All the time, energy's got to be put into this system. I'm going to guess, you guys probably already know this, where does all the energy that fuels biological systems initially come from? Hopefully you said the sun. All of the energy that fuels our ecosystems ultimately comes from the sun. So Energy is the capacity to do work. One form of energy can be converted to another. You think of a light bulb, takes electrical energy, converts it into thermal energy. We have light energy, heat energy, electricity, motion is kinetic energy, all that kind of stuff. In chemical bonds, it's actually potential energy. So there's a lot of energy there that has the potential to do work. It's just the energy of position. It's currently bound up right now. But as we break those bonds, we do release that energy. And we can store that energy for later, which makes chemical bonds very useful for plants and animals as a energy storage system. So when it comes time to disperse energy, we have a couple laws we have to be respectful of. The first is the first law of thermodynamics, which is energy is neither created nor destroyed, but it can be transferred from one form to another. So we can't make energy from nothing. We can't make energy cease to exist, but we can convert chemical energy in gasoline into kinetic energy in a tire, something like that. We can convert them from one form to another. So our second law of thermodynamics is often called the law of entropy. Entropy is a measure of the disorder in a system. And entropy, the general rule is entropy is always increasing. So we're always increasing disorder. The entropy of two atoms is going to decrease if they form a bond, so they're becoming more orderly. And every time you have an energy transfer, little bits of it disperse, and the universe, I guess you could say, becomes more disorderly, increasing entropy. So another way of saying this is there's really no such thing as 100%. When we do energy transfers, you're always going to lose a little bit of energy. That's the second law of thermodynamics. So this is the energy flow for life. Here is energy flowing in, and the sunlight is what's coming down to our producers, our plants and our algae, and they capture some of that energy. And then from the producers, some of that energy is lost to the environment as just, heat and waste. And some of that energy is converted to consumers when the consumers eat the plants. So the consumers, deer and cattle and fish and us, some of that energy passes right on through us. We don't ever return it to the sun, so there's really not a closed system. It's a one-way flow, sun to producers, producers to consumers, consumers out. That energy is lost. That's the second law of thermodynamics. If we were able to restore 100% of our energy back to the sun, then we'd have a closed ring, but we really don't. So some of this matter is recycled between consumers and producers, the whole circle of life thing. The consumers die and the decomposers break them down, and then the plants take their minerals up in the roots, that kind of stuff. We do get some cyclical nature here, but for energy, there's not a lot of exchange. It's just mostly wasted and transferred from the sun through the system. So it is important to kind of understand the difference in the cyclic nature of matter and the very linear nature of energy. So let's look at a few other things that we need to know about molecules and energy. Reaction. Please tell me you know what a reaction is at this point. A chemical change that occurs when atoms interact, right? We know that. And we have reactants and products. Reactants is everything on the left side of an arrow. Molecules that enter the reaction. The product is everything on the right side of the arrow. What is left over at the end of the reaction? So here it is. Reactants get together to make products. Not too terribly complicated. Chemical bonds and their energies is where we get to a little more biological application. All of our cells are going to store and retrieve energy in these chemical bonds of the molecules of life: proteins, lipids, carbs, nucleic acids. By comparing bond energies of reactants and products, we can predict whether a reaction is going to require energy or if it's going to release energy. If it's going to require energy and we're going to have to put energy into that reactant side to get things going, we call those endergonic. So energy needs to go in. If this is releasing energy and the reactants will go on their own and the products are releasing lots of energy, we call this exergonic, or energy out. Those are the differences between those two. And so here we have free energy increasing. we take our carbon dioxide and our water and we make glucose. This is endergonic. We're taking energy in. And then we burn that glucose with oxygen and we make carbon dioxide and water. That is energy out, or exergonic. These two need to be going on both at the same time, and a lot of times in one organism at the same time, for the case of plants, to be making energy and burning energy at the same time to kind of stay alive. So that's a good example there. Your book has this weird little part about why the earth doesn't go up in flames. I don't know if it's really that amazing, but there you have it. Basically, their argument is, hey, a stick is cellulose hydrocarbon, and if you strike a match, the stick will burn. Our whole world is made of plants, which is cellulose and hydrocarbons. Why doesn't the whole world burn? Well, I don't know. If you're in Wyoming or South Dakota or California in the summer, it can from time to time. We have huge fires, but their idea is the whole earth doesn't burn because there's not enough activation energy to maintain fire throughout the whole planet, which is great, I guess. That's good. But here it is. Activation energy is to get a reaction started, you need some energy inputs. So the minimum amount of energy needed to get your reaction started, that's the activation energy, to get those reactants to start turning into products. Some reactions require a lot of activation energies, others not so much. Here's a diagram. I would guarantee you've seen this in Gen Chem, but here it is. Free energy, reactants on the left, products on the right. The reactants are not reacting just yet, but it takes a certain amount of energy to break and reform these bonds, and when that occurs, we get an increase in energy, and we call that our activation energy. Then they go down, 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 down to a more energetically favorable product that is more stable than the original reactants, hopefully. But the difference here, this is looking like an exergonic reaction, is we've got to get over this little speed bump called the activation energy. And for human metabolism, it's important that we do this quickly. So, energy in, energy out. Small molecules, energy in, we can build up big organic compounds like carbs and fats, and we can store that energy for later. Then when we need it, we can take these big organic compounds, use them as exergonic reactions, get that energy out of our food, and break them down into small molecules like carbon dioxide and water, which we can just exhale. So when it comes to our digestion, animals and cells and you and I, we're really focusing on enzymes. Those are the workhorses of our metabolism, and they help us through a process called catalysis, which basically means to catalyze or to speed up. So an enzyme makes a specific reaction occur a lot faster than it would on its own. Enzymes are cool because we're not consuming them and we're not permanently changing them by participating in a reaction. So they're not a reactant, they're not a product, they are an enzyme. They speed up a reaction, they're a catalyst. Most of these guys are made out of protein. There are a few that are RNA based, and what they're going to do is make a reaction that would normally take forever take just a fraction of a second, and they're the reason we can digest food and stuff like that. So enzymes have to act on a substrate. A substrate is the specific reactant acted upon by an enzyme. Oftentimes it's given with a lock and key example. The substrate is the key that fits the lock, which is the enzyme. And there are enzymes just for fats, and there are enzymes just for proteins, and there are enzymes just for carbs, and you get the idea. They're very specific. So catalysis, to catalyze, lowers activation energy. So why do enzymes make reactions faster? They function by lowering the activation energy of a reaction. So they're going to bring on what's called a transition state, and the substrate bonds break real easy, and the reaction runs spontaneously from there. And so they might make two molecules face the direction they need to make a bond occur, or they might physically pull apart two molecules that might not want to be pulled apart that readily. And so these are all ways enzymes can catalyze a reaction. They have active sites. Active sites are the location where the substrate binds. So if the if the enzyme is the lock, and the substrate is the key, then the active site is the keyhole that the substrate must find. These guys are complementary in size, shape, polarity, and charge to the substrate, which basically means they are a nearly perfect fit. If the substrate is negatively charged, the enzyme will be positively charged, so it just pulls it right in there. So when we look at enzyme-mediated reactions, the substrate's going to bind at the enzyme active site. It can bring on that transition state by a few different mechanisms. One, that enzyme could physically just bring two substrates together and kind of push them together and say, make a bond. You know, you're facing the right direction, make a bond. The other option is to orient substrates in positions that favor the reaction. So grab two substrates, one's facing the wrong way, the enzyme turns it around, pushes them together, we've got a product now. And then the other is inducing a fit between the enzyme and the substrate, or an induced fit model. This is a little different. This is where the substrates don't quite fit and the enzyme doesn't quite fit, so the enzyme will actually flex and change shape just a little bit to make things work to get that reaction done. And then the last one is really kind of creative. Really everything we're going to see for digestion is pretty much going to exist in water. You know, blood plasma is a lot of water, digestive fluids are a lot of water, and some enzymes will get water out of the way, get water out of the picture so that these two molecules can interact without being surrounded by water, and that can speed a reaction up a lot as well. So 4 big ways that they work. Enzymes are important, but they are a little bit picky. You know, they're designed to work in you, and you have a pretty specific set of temperature range, pH range that your body's going to function best at. So if we raise that temperature a little bit, we can boost our reaction rates by increasing our free energy. But if we get too hot, our body can cause these enzymes to actually denature. So it's not good to have too high of a body temperature. Each enzyme has an optimum pH range. Most of our enzymes in people are going to work 6 to 8. You know, they'll be okay. And for your blood plasmas and most of your body fluids, that's about what you're going to be at, except for places like, you know, the stomach, of course, would be very acidic, and the duodenum and the small intestine would be pretty basic at first. So it's just some stuff like that. And then, of course, salt levels as well. They affect hydrogen bonds that hold enzymes in their 3-dimensional shape. And so we can't be too salty, we can't be too hot, we can't be too cold, we can't be too acidic, we can't be too basic. Enzymes have an optimal range that they behave best at. And that's why our body is so consistent at maintaining homeostasis so well for our body temperature. So it works well. Okay, so metabolism, enzyme-mediated reactions is actually where we're going to stop for this one, because I want to give you a break before we jump back into metabolic pathways, because it gets we kind of build off of this basic enzyme idea into some more complicated stuff. So let me show you a quick video on enzymes, and then we are going to call it good.
When substrates first settle into the active site, they don't quite fit. This places a strain on some of their bonds. This strain forces the substrates into an activated transition state. The transition state allows the tightest binding between the enzyme and substrate, but it is unstable. New stable bonds form and the product is created. The enzyme is unchanged by the reaction.
Okay, there you have it. Quick notes here. This is not what an enzyme actually looks like in your body. Not even close. They're way more complicated than this. This is a cartoon version, right? We have an enzyme with a big circle and a little circle because it fits a big circle and a little circle. The enzyme changes shape a little bit, facilitates this bond right here, and we've made a product. It's the dumbed down cartoon version, but it is the idea of an enzyme that fits a specific substrate and then makes a specific product. So not a bad place to start for metabolism. We'll call it there, guys. Thanks.